In this video, we're going to be looking at how pH actually changes throughout the course of a titration, because it is not linear at all. So in the titrations that we have done in the lab, we've been using a pH indicator to tell us when to stop, to tell us when neutralization has been achieved, when we have added exactly enough titrant to neutralize our analyte. But there is another way that we can determine that if we're able to monitor how the pH changes throughout the experiment. So if you have a digital pH meter, you can keep that in your solution as you go and monitor the pH. And if you produce a graph of that data, we call it a titration curve. So this is just a plot of how the pH changes throughout a titration. Specifically an acid-base titration. There are other types of titrations that we can do. But if we're doing an acid-base neutralization reaction in our titration, monitoring the pH is a great way to keep track of what is going on. So we can find our equivalence point on the graph instead of relying on a pH indicator. So what we are looking for is that near our equivalence point, which is where we typically end our titration, so let's actually define that. Our equivalence point is when exactly enough of our titrant, whatever is in our burette, whether it be acid or base, has been added to neutralize the analyte, which is whatever's in your flask, with no excess. So this is what we are assuming when we're doing our titration calculations, is that the volume that we added is the volume it took us to get to the equivalence point. This is actually slightly different than what we are actually detecting with a pH indicator, which is our endpoint. Our endpoint is when our pH indicator changes colors. In a well-designed titration, if you are using a pH indicator, your endpoint and your equivalence point will be very, very close together. So at our equivalence point, our pH is actually changing most rapidly. So our equivalence point ends up being an inflection point for the graph. So this is where our pH is changing very quickly. So we have a very, very steep slope at that point. So our equivalence point is at the point where we have the steepest slope, which is at the inflection point of the graph. So if we want to sketch what a titration curve will actually look like, it's going to change a little bit depending upon whether we're dealing with strong or weak acids or bases. So if we are titrating a strong acid with a strong base, we will get a graph where pH is our y-axis and the volume of base added is our x-axis. And if we want to sketch the curve that we would get, since we are starting with a strong acid, before we add any base, so this is when nothing has been added yet before our titration has really started, we would expect the pH to be low since we're starting with an acidic solution and adding base into it. And then as we begin to add base, we would see the pH begins to increase. And it is more or less linear for a while until it's very much not. So at some point you'll see a very sharp increase, a very nearly vertical section of your graph that represents the area around your equivalence point. So right at the middle of this, close enough, would be where your equivalence point actually lies. So from this, we can read the volume it took. So this volume here would be the volume it took us to reach our equivalence point. And using that volume, we can do all of the typical titration calculations that would allow us to calculate a concentration of an unknown. So if we didn't have a pH indicator available or we didn't know what an appropriate pH indicator to choose would be, as long as you have a pH meter and you can graph the pH versus the volume of base added, you can identify your equivalence point this way and get your volume in a different way. If we are starting with a strong base solution and titrating it with a strong acid, we would get essentially the same thing flipped upside down. So since we're starting with a strong base, we would expect to start out with a pH that is high. And as we're adding an acid into it, we would expect to see the pH decrease more or less linearly until it's really bad. It sharply drops near our equivalence point. So we can see we just kind of flipped that first graph upside down. So our equivalence point would be right about in here. For this one. So if we have a weak acid or a weak base involved, it looks a little bit different. Actually, one other thing I wanted to mention before we move on. For these titrations, for a strong acid with a strong base, the pH of our equivalence point in both of these cases, my axes are a little wonky, but the equivalence point always occurs at pH 7. If we think about the reaction that is going on in both of these in terms of the net ionic equation for a strong acid plus a strong base is always the same, is always hydronium plus hydroxide producing water. All we're making here is water, which is neutral. So when you have added exactly enough base to react with all of your acid, all that you have is water and any spectator ions that may be around, but there's nothing else really in there that could be affecting the pH. So for strong acid, strong base titrations, the equivalence point always occurs at pH 7, which is kind of nice. So with weak acid or weak base involvement, so if we're starting with a weak acid and you're titrating with a strong base, The shape is going to be similar to the strong acid, strong base, but there's one little distinct feature that can actually help us tell if we, say, don't know what acid we're titrating, can help you determine if it's strong or weak. So in our strong acid, strong base titration, we see this first little section here is more or less linear. It's pretty straight. But if your acid is weak, we actually see a little kind of shoulder at the beginning. And then the rest of it looks more or less the same. We still have that equivalence point feature that looks pretty similar. But for a weak acid, this very first portion is just a little bit curved, which can help you tell when you're looking at a titration curve what kind of acid or base was involved. So for these guys, we once again have our equivalence point in the middle of that really steep section. And the pH of these is actually not neutral. So although we have achieved neutralization, that doesn't necessarily mean that your pH of your solution is going to be neutral. For a weak acid with a strong base, the pH is actually going to be slightly greater than 7 at the equivalence point. I'll talk a little bit more about this in a later video. But what's actually happening in this titration is that one of your products is a weak base. So when you reach the equivalence point, you've consumed all of your weak acid, you've consumed all of your strong base, but one of the products you've created is a weak base. So it makes the solution slightly basic. The opposite will be true for a weak base with a strong acid. So again, we're kind of going to just flip the previous one upside down, that we're starting with a base. So we would expect the pH to be high. We'll see the same sort of little curve at the beginning before it becomes more or less linear. The equivalence point happens somewhere and then it keeps on going. So we've got our equivalence point here. And the pH at the equivalence point for this combination is going to be somewhat less than 7. So similarly to the previous one, in this case, when you get to your equivalence point, you have used up all of your weak base, you have used up all of your strong acid, but one of the products you have produced is actually a weak acid. So again, we'll kind of come back to this again later. But at your equivalence point, you have produced water and a weak acid, so your solution will actually be slightly acidic, despite the fact that we have neutralized our original sample. So again, we also have this little sort of curved portion that helps us tell the difference between the strong base, strong acid versus the weak base, strong acid. So when we see that this little section here is curved, means that there is something weak involved in this reaction. When this first little section is straight, means that both the acid and base involved in that titration are strong. So weak acid with weak base titrations are not commonly done because those don't necessarily go to completion. Depending upon exactly how weak your acid and base are, they may establish an equilibrium that is not really all that product favored. The reason why we're able to do what we're able to do with titrations and the calculations that we do is because we're assuming these reactions go to completion. Their equilibrium constants are in the like millions, billions, trillions kind of territory. They're really, really huge. So we can assume that our limiting reactant is completely consumed, which allows us to do the stoichiometry that we need to do in titration calculations. So weak acid with weak base or vice versa is not a combination that you'll need to worry about.